Deep beneath the Earth's surface, shielded by kilometers of solid rock and suspended in vast tanks of ultra-pure water, multi-ton vats of liquid xenon have been maintained at cryogenic temperatures for years. These subterranean facilities, isolated from the ceaseless bombardment of cosmic rays, were constructed with a singular, highly specific purpose: to capture the faint, momentary flash of light produced when a weakly interacting massive particle, or WIMP, collides with a xenon nucleus. For 4 decades, the standard cosmological paradigm has dictated that the missing mass of the universe must be composed of such undiscovered quantum particles. Theoretical physics demanded their existence. Extensions to the standard model, particularly supersymmetry, predicted them with mathematical elegance. Billions of dollars and countless hours of computational analysis have been dedicated to refining the sensitivity of these detectors, pushing the boundaries of experimental physics to levels that would have registered the leading candidate particles many times over. The result of this unprecedented global scientific effort has been a profound, uncompromising silence. Empty detectors, empty data sets, a completely null result across the entire predicted parameter space. This sustained empirical failure forces a rigorous reevaluation of the foundational assumptions governing modern astrophysics. If the missing mass is not a new, exotic particle awaiting discovery in a subterranean tank, the alternative is almost more unsettling. The solution may not require new physics at all. It may rely on a phenomenon that general relativity predicted over a century ago, an object that has been directly observed, precisely measured, and mathematically defined. The missing mass might simply be a population of primordial black holes, formed before any other structure in the universe existed, drifting through the cosmos, invisible to every electromagnetic instrument ever built, yet gravitationally present in exactly the quantities the dark matter problem requires. The hypothesis that dark matter could be composed of black holes is not a recent fabrication. Stephen Hawking himself explored the mathematical viability of primordial black holes in the early 1970s, shortly after his foundational work on their formation mechanisms. However, for nearly half a century, a severe theoretical objection kept this hypothesis relegated to the absolute margins of serious cosmological debate. That objection was Hawking radiation. In 1974, the same physicist who proposed the existence of primordial black holes discovered a quantum mechanical property that seemed to guarantee their destruction. Black holes are not perfectly black. The intense gravitational gradient near the event horizon polarizes the quantum vacuum, leading to the spontaneous creation of virtual particle-antiparticle pairs. When one particle falls past the horizon, while its partner escapes to infinity, the black hole loses an equivalent increment of mass energy. They radiate thermally, leaking particles into space. The mathematics governing this emission dictate a strictly inverse relationship between a black hole's mass and its temperature. The smaller the black hole, the hotter it burns, and the faster it radiates its mass away. As the mass decreases, the radiation accelerates, creating a runaway feedback loop that ends according to the standard semiclassical approximation, with the complete evaporation of the singularity in a catastrophic final burst of high-energy gamma radiation. For primordial black holes lighter than roughly 10 to the 12th kilograms, approximately the mass of a small terrestrial mountain, this evaporation timescale is strictly shorter than the current age of the universe. According to this framework, any low-mass primordial black holes forged in the Big Bang should have dissolved entirely into background radiation billions of years ago. This mathematical certainty appeared to permanently close the door on the lightest primordial black holes as viable dark matter candidates, leaving only the heavier mass windows, which were subsequently constrained and largely ruled out by gravitational lensing surveys and precise measurements of the cosmic microwave background. Then, the theoretical framework shifted. In 2024, a groundbreaking study published in the monthly notices of the Royal Astronomical Society fundamentally altered the evaporation paradigm by incorporating the mechanics of quantum gravity near the terminal endpoint of a black hole's life. The standard Hawking calculation relies on the assumption that the space-time manifold remains perfectly smooth and continuous, all the way down to the central singularity. However, multiple robust theoretical frameworks of quantum gravity, most notably loop quantum gravity, mathematically demonstrate that space-time must become discrete at the absolute smallest scales. There exists a fundamental minimum resolution to reality, known as the Planck length, measuring approximately 1.6 times 10 to the negative 35th meters. Below this precise metric, space cannot be meaningfully subdivided. When this discrete, quantized geometry is applied to the event horizon of an evaporating black hole, the behavior of Hawking radiation changes drastically at microscopic masses. The temperature curve is no longer allowed to diverge to infinity. As the black hole shrinks toward the Planck scale, its temperature reaches a maximum threshold and then precipitously falls. The evaporation rate decelerates, asymptotically approaching zero. The black hole does not detonate, it does not vanish. It settles into an eternally stable microscopic remnant. In 2025, a separate, highly credentialed team led by physicist Paul Davies published an independent, rigorous analysis in Physical Review D that arrived at the exact same conclusion through a completely different mathematical methodology. By introducing a generalized uncertainty principle that enforces a fundamental minimum length into the thermodynamic geometry of the black hole, they proved that the Hawking temperature is naturally regulated. The catastrophic runaway divergence simply does not occur in a quantized spacetime. The endpoint of evaporation is a stable, zero-temperature remnant that no longer radiates, no longer decays, and endures permanently for the remainder of cosmic time. If these quantum gravitational models are accurate, the smallest primordial black holes did not evaporate into nothingness. They shrank, they cooled, and they reached a state of indestructible equilibrium. They are still out there, not in small clusters, but in unimaginable quantities. Trillions upon trillions, possibly quadrillions, scattered across the vast, invisible halos of every galaxy in the observable universe. Each individual remnant would be lighter than a mountain, smaller than a single proton, yet carrying an exact, immutable unit of gravitational mass. Because they exist at the Planck scale, they possess absolutely no electromagnetic cross-section. They do not emit light, they do not absorb light, and they interact with baryonic matter exclusively through the curvature of spacetime. The term that most accurately describes this theoretical population is a swarm. This is not a diffuse cloud of exotic quantum particles drifting like a fluid through the interstellar medium. It is a swarm of discrete, localized singularities. Each one is an infinitely dense knot of spacetime forged in the primordial plasma during the first fraction of a second of cosmic history. Each one is older than the heavy elements, older than the first stars, and vastly too small to register on any particle detector humanity has ever constructed. Yet, collectively this swarm performs exactly the gravitational labor required of dark matter. It clumps within deep potential wells. It forms the massive halos that dictate galactic rotation curves. It traces the exact large-scale filamentary structure of the cosmic web. It provides the exact missing mass, not through unproven extensions to the standard model, but through the extreme compression of reality itself. This theoretical resurrection of primordial black holes would remain a mathematical curiosity, if not for the sudden, unprecedented convergence of observational data. The November 2025 gravitational wave detection, cataloged as S251,112 centimeters, provided the first empirical anchor. The chirp mass of the merger, sitting firmly below the Chandrasekhar limit, is perfectly consistent with the merger of two primordial black holes that formed specifically during the quantum chromodynamics phase transition. At approximately 10 microseconds after the Big Bang, the universe expanded and cooled just enough to allow free quarks and gluons to bind into the first protons and neutrons. This sudden phase transition caused a temporary, microscopic drop in the pressure of the primordial plasma, softening the equation of state and drastically lowering the threshold for gravitational collapse. The mass distribution predicted to emerge from this specific microsecond of cosmic history peaks precisely in the subsolar mass range, exactly where the LIGO network recorded its anomalous signal. Furthermore, the extreme rarity of this detection is not a deficit of the model. It is a strict mathematical prediction of it. The Capelluti team's comprehensive analysis demonstrated that if the dark matter halo of the Milky Way is populated by these ancient singularities, their velocity dispersion and spatial distribution would result in an incredibly low merger rate in the local universe. At the current sensitivity constraints of the LIGO-Virgo-Cagra network, the statistical expectation is roughly one detectable subsolar mass merger every few years. In an operational history spanning a decade and encompassing over 300 confirmed stellar mass mergers, the observatories have recorded exactly one subsolar candidate. The math aligns perfectly. The rarity is a direct signature of a vast, ancient, stabilized population drifting through the galactic medium. Simultaneously, a completely independent domain of observational astrophysics has begun accumulating evidence that points relentlessly toward the exact same conclusion, emerging not from the localized ripples of spacetime, but from the ancient, redshifted light of the early universe. When the James Webb Space Telescope achieved orbital insertion and began delivering its first deep-field infrared data in 2022, the cosmological community anticipated observing a universe in its infancy. The established lambda cold dark matter model predicted that the first few 100 million years following the Big Bang would be characterized by slow, hierarchical assembly. The data was expected to reveal small, faint proto-galaxies, irregular clouds of pristine hydrogen and helium gradually collapsing to form the first population 3 stars, which would then slowly cluster over billions of years to build the massive galactic structures we observe in the local universe. The data returned by JWST violently contradicted these standard predictions. The early universe was not under construction, it was already heavily industrialized. Galaxies observed at extreme redshifts, existing when the universe was merely a few 100 million years old, were not faint, irregular protostructures. They were massive, highly luminous, and structurally mature. They exhibited defined disks, established stellar populations, and a mass assembly that defied the timeline of the standard cosmological model. At the gravitational centers of these impossibly early galaxies sat objects that posed an even more severe theoretical crisis: supermassive black holes. These were not modest stellar remnants, but monstrous singularities containing millions, and in some cases billions of times the mass of our Sun. They were actively accreting vast quantities of primordial gas, powering quasars so intensely luminous they outshone their entire host galaxies, all existing at an epoch when the universe was less than 1 billion years old. The fundamental problem with these observations is a matter of strict astrophysical arithmetic. In the standard paradigm, supermassive black holes are not born, they are grown. They originate as relatively small stellar mass seeds, roughly 10 to 100 solar masses, left behind by the core collapse supernovae of the very first massive stars. These seeds must then grow by merging with other black holes and by continuously accreting surrounding gas. However, this accretion process is governed by a strict, immutable physical constraint known as the Eddington limit. Formulated by the English physicist Arthur Eddington in 1926, this limit defines the maximum rate at which a black hole can consume matter. As infalling gas spirals into the accretion disk, intense, viscous friction heats the material to millions of degrees, generating a massive outward flux of electromagnetic radiation. The Eddington limit is the exact equilibrium point where the outward pressure of this radiation perfectly counterbalances the inward pull of the black hole's gravity. It acts as a hard speed limit on mass accumulation. If you apply the mathematics of the Eddington limit to a standard stellar mass seed, the timeline collapses. Even if a 10 solar mass black hole were placed in an environment with an infinite supply of gas, and even if it accreted matter continuously at the absolute maximum Eddington limit without a single interruption, it requires roughly 1 billion years of exponential growth to reach a mass of 1 million solar masses. Yet, JWST has definitively identified supermassive black holes weighing hundreds of millions of solar masses existing less than 500 million years after the Big Bang. The chronological arithmetic simply does not function. There is physically not enough time in the age of the universe at that redshift for stellar seeds to have grown to such monstrous proportions. The crisis deepened in late 2024 with the JWST observation of a high redshift quasar designated LID 568. Existing just 1.5 billion years after the Big Bang, initial spectroscopic analysis indicated this object was accreting matter at a rate 40 times greater than the theoretical Eddington maximum. While subsequent refinements in 2025 suggested the accretion rate may have been slightly overestimated due to complex outflow geometries, even the most conservative revised estimates place LID 568 in a regime of extreme super-Eddington accretion that the Standard Model struggles to physically accommodate. The object was absorbing mass with a violent efficiency that textbooks dictate should blow the surrounding accretion disk apart. Further anomalies compound the issue. JWST has identified supermassive black holes situated between early disk galaxies, completely lacking a host galaxy of their own, with no kinetic signature or ejection trajectory to suggest they were expelled from a massive merger event. They appear to have formed in situ, directly from the gravitational collapse of enormous primordial gas clouds, entirely bypassing the prerequisite stage of stellar formation. Additionally, the telescope analyzed a system cataloged as QSO-1, a mature supermassive black hole residing within a host galaxy possessing an extremely low metallicity. The galaxy contained less than 1% of the oxygen abundance found in the modern Milky Way. Because heavy elements like oxygen are synthesized exclusively in the thermonuclear cores of stars and distributed via supernova over successive generations, the near-total absence of these elements proves that almost no stellar evolution had occurred in that galaxy before its central supermassive black hole began to actively feed. Whatever mechanism forged these colossal singularities, it was fundamentally disconnected from the life cycle of stars. The stars had not yet had the time to live, die, and seed the cosmos with heavy elements, yet the supermassive black holes were already present, already massive, and already dominating their local gravitational environments. Every independent line of observational data from the early universe points toward a singular, inescapable conclusion. The cosmos contains supermassive black holes that could not possibly have grown from stellar remnants in the brief chronological window available. They must have been created by a mechanism that operated before the first stars ever ignited. If the universe produced primordial black holes at the massive end of the spectrum that Hawking's analysis described, possessing hundreds of thousands of solar masses mere moments after the Big Bang, these ancient singularities would have served as the immediate gravitational anchors around which the very first structures of the cosmos were forced to assemble. They would not have required the agonizingly slow, incremental accumulation of baryonic matter from stellar remnants. They were already staggeringly massive when the primordial hydrogen cooled sufficiently to permit the first atomic formations. These supermassive black holes that the James Webb Space Telescope is currently identifying at the gravitational centers of impossibly early galaxies would not be the product of billions of years of standard accretion physics. Instead, they represent the direct, unbroken descendants of objects that precipitated out of the quantum density fluctuations in the very first second of cosmic history. We are now witnessing the convergence of two monumental pillars of observational evidence, arriving from completely independent methodological vectors. One pillar is constructed from the data of the most sensitive interferometric instruments ever engineered, listening to the infinitesimal deformations of space-time itself and detecting a merger involving a primary mass far too diminutive to have been forged in the collapse of a star. The second pillar emerges from the largest infrared observatory ever deployed into the vacuum of space, peering back at the earliest epoch of galaxy formation and finding supermassive black holes far too colossal to exist at such an early cosmological date. Both of these rigorous lines of inquiry converge upon a singular, mathematically elegant conclusion. The universe has been carrying a vast population of non-stellar black holes since its first second of existence. If these primordial black holes populate the cosmos across the vast mass spectrum that these combined observations suggest, then the implications extend far beyond resolving the 90-year-old dark matter discrepancy. The exact same population of ancient singularities that accounts for the missing kinematic mass in galactic rotation curves, and the exact same population that explains the impossibly rapid assembly of the earliest galaxies, would have fundamentally dictated the macroscopic architecture of the universe itself. We are speaking of the underlying scaffolding upon which all visible baryonic matter has been deposited. The cosmic web, the vast interconnected filaments of galaxies, and the colossal superclusters that define the large-scale structure of everything we have ever observed, would be the direct result of this primordial gravitational framework. The gravitational architecture was constructed first. The baryonic illumination arrived second. The stars did not build the universe. They merely migrated into a structure that was already standing. It is a cosmic architecture constructed by objects that precipitated from the primordial plasma, and these objects have been maintaining the structural integrity of the galaxies ever since. They remain invisible, utterly silent across the electromagnetic spectrum, and older than any other structured entity in existence. To understand the immediate physical reality of this hypothesis, one must consider the spatial distribution of these objects in the present epoch. They are not relegated to some unobservable corner of the high redshift universe. They are here, distributed throughout the Milky Way, constituting the vast spherical dark matter halo that envelops our galactic disk. If primordial black holes are indeed the primary constituent of the missing mass, then the solar system itself is currently embedded within a diffuse, drifting cloud of these ancient singularities. At the lowest end of the theoretical mass spectrum, the stabilized Planck scale remnants would possess physical dimensions smaller than an atomic nucleus. You would not detect one passing directly through your biological tissue. It interacts exclusively through the gravitational force, and its influence at such a microscopic mass and transient proximity would be immeasurably small, far below the threshold of any local instrumentation. Yet, according to the mathematical models governing dark matter distribution, it would be there. A discrete singularity, older than the Earth, older than the Sun, and older than the Milky Way itself, passing through the very space you currently occupy. Spatially, within the calculated volume of the solar system, and statistically within the volume of your immediate surroundings, they are passing through without interaction, without electromagnetic emission, and without triggering any detector currently capable of registering their individual presence. We are presented with a reality where the oldest objects in the universe share the exact same spatial coordinates as the youngest biological structures on Earth. The methodological question of how to empirically confirm this invisible presence will define the next generation of astrophysics. Gravitational wave interferometry remains the most promising and robust avenue for direct confirmation. The Laser Interferometer Gravitational Wave Observatory's detection of the subsolar mass candidate in November 2025 serves as the critical opening act in this new era of observational science. Because no known stellar collapse mechanism can mathematically produce a black hole below the Chandrasekhar limit, a subsolar mass black hole is, by definition, primordial. The physical logic is exceptionally clean. However, the scientific method does not construct massive theoretical frameworks upon single, isolated data points. Rigorous confirmation necessitates a statistically significant catalog of detections, mapping directly to the predicted mass distribution from quantum chromodynamics phase transition models. The observational infrastructure is rapidly evolving to meet this exact demand. The LIGO Voyager upgrade, projected for deployment in the late 2020s, will introduce substantially heavier mirrors and higher frequency laser systems. Following this, the proposed Cosmic Explorer, featuring vacuum arms spanning 40 kilometers, would achieve a sensitivity approximately 10 times greater than the current advanced LIGO configuration. Simultaneously, the space-based Laser Interferometer space antenna will monitor an entirely distinct frequency band. Beyond gravitational waves, a second robust line of empirical evidence relies on the physics of gravitational microlensing, the Vera-C. Rubin Observatory will monitor billions of stellar sources with a temporal cadence and photometric sensitivity that utterly dwarfs all prior legacy surveys, poised to definitively expose halo populations. A third empirical avenue involves the precise analysis of the cosmic microwave background, where future observational missions like CMBS-4 will push polarization constraints to their fundamental limits. A fourth, highly exotic observational possibility hinges on the reality of Hawking radiation. If primordial black holes with initial masses precisely near the critical evaporation threshold are currently completing their quantum evaporation cycles in the modern universe, their final moments should be characterized by detectable, catastrophic bursts of high-energy gamma radiation. Anomalous data points continue to emerge, such as the extraordinary 120 peta-electron-volt neutrino event recorded by the CAM3 net detector deep in the Mediterranean Sea. While unconfirmed, one of the leading theoretical explanations for this immense energy spike is the terminal quantum evaporation of a primordial black hole. It perfectly mirrors the historical pattern of astrophysical breakthroughs. New instruments inadvertently detecting the unexpected signatures of phenomena that have always been present. If the existence of primordial black holes is empirically confirmed, the cascading consequences will fundamentally rewrite observational cosmology. The decades-long search for a weakly interacting massive particle would be recognized as a highly accurate null result that was simply misinterpreted as silence. The subterranean detectors functioned flawlessly. They detected nothing because the missing mass was always a vast, ancient population of macroscopic gravitational objects. This realization forces a profound philosophical recalibration regarding the ultimate nature of reality itself. If the oldest objects in the universe are indeed black holes, then the very first structures forged by reality were absolute prisons, regions of space-time from which absolutely no information or matter can ever escape. The universe's inaugural creative act was not the emission of light, but the enforcement of absolute darkness. It was not an act of expansion, but of infinite containment. Before the first photon of the cosmic microwave background decoupled from the primordial plasma, the universe had already manufactured objects defined entirely by what cannot leave them. Stars, planetary systems, oceans, atmospheres, and the biological civilizations that observe them are fundamentally temporary structures. The primordial black holes, however, endure. They have maintained their structural integrity since the first second of time, and they will persist long after the final star exhausts its nuclear fuel, slowly evaporating over timescales that render the current age of the universe as nothing more than a single fleeting frame in an infinitely long cinematic projection. They're the absolute first things the universe manufactured, and they will be the absolute last things it contains. We reside within a cosmos built upon an immutable scaffolding of invisible, ancient singularities. These objects dictated the precise formation of the galaxy you inhabit billions of years before the galaxy itself existed. They are passing through the local space around you at this very moment, carrying the immense gravitational memory of the first second of time. You have spent your entire existence inside a vast structural framework held together by entities you cannot see, governed by extreme physics. We are only now beginning to mathematically model. The universe constructed the darkness first, and the darkness remains the permanent frame upon which the temporary light is hung. In 1933, Fritz Zwicky looked at the anomalous velocities within the Coma cluster and asked where all the missing mass was located. Decades later, Enrico Fermi questioned the apparent absence of advanced cosmic structures. Now, advanced interferometry may have finally answered Zwicky's 90-year-old question with an infinitesimal ripple in space-time, produced by two compact objects that standard stellar physics dictates should not exist. The oldest entities in the cosmos, colliding in the absolute dark, sent a gravitational signal through the fabric of reality that arrived precisely when we were finally ready to listen. The answer to the dark matter discrepancy was always there, hiding in the extreme thermodynamics of the first second. It is a solution older than the stars, smaller than a subatomic particle, vastly heavier than a mountain, and permeating the space all around us right now, in the absolute dark.